Today's topic is triple integrals in Cartesian. When you see Cartesian like this, you know right away that we are back to x and y variables, which might be good news to some of you, because to many of us, working with x and y is far more intuitive than working with radius and angle. Today is going to be about the triple integrals, and we need 3 variables for that. So you work with triple integrals, you need 3 variables, which means that x and y that we have right here is not going to be enough for today. We need one more, and of course that should be z. So let's get started now. I am going to start with the double integrals, something that we have spent many hours on in the past few weeks. So let's start right here, double integrals. When you work with double integrals, you have 2 variables. So you have 2 variables. And most of the time you have this x and y for Cartesian form. And sometimes you have this r and theta for polar form. But today we are going to stick with the Cartesian form, x and y. So we had something like this in the past few weeks. We had this double integral, alright, of a multivariable function f with, of course, 2 variables, x and y. And we performed the double integration with respect to differential area, dA, over an integration domain of R. Okay, so we had something like this. And let's talk about this dA right here really quickly. This dA, by now we know that this is the area of a small piece in the integration domain. So it comes from this. One small step in x direction, like this. This is dx, okay? And one small step in y direction, and it goes like this. This is dy, and when you combine them, it becomes this rectangle. Okay. And the area of this rectangle is dA, which means that the dA is going to be equal to the product of dx and dy. Either dx dy or equal to dy dx. Same area, right? You can make a note right here that this dA is the area of small piece in integration domain R. You just took one small piece out, and that is dA. So let's take a look at this. R right here, this is the integration domain. R stands for region, which means that the integration domain for the double integral is going to be 2-dimension region, 2D. And you see dA right here, differential area. Area has to be 2-dimension. So let's make a note that this is 2D. Now we perform the double integral on this function, and we have some physical meaning to this double integral. And it corresponds to this. I hope you can still remember that. It corresponds to the volume. Okay, equal to the volume under the function surface, under surface of this function x and y, f of x and y, and not just about the volume under the surface. It has to be over a certain base, which is the integration domain R, over integration domain R. Okay, now let's take a look at this. Volume right here. When you see something like this, you know this is something in, it's a quantity in 3 dimension. Okay, so the result of this double integral becomes a quantity in 3 dimension. But I want you to keep in mind that when it comes to double integral, it doesn't have to come out to be something in 3D. It can come out to be something in 2D as well when you do something like this. So we did this in the last lecture, maybe 2 lectures away. We assigned this function to be equal to 1. Alright, we did this. Right here we assigned f of xy to be equal to 1. And when we do this, the physical meaning of this double integral becomes the area. Okay, so this becomes area of the integration domain R. Okay, so in this case, this double integral corresponds to a quantity in 2 dimension. Alright, so I just want to point out that when you perform a double integral, it doesn't have to be 3D always. Sometimes it can be 2D as well. Right? It depends on how you use it. Okay, either in 3D quantity or 2D quantity. Right, now let's move to triple integrals. Of course, in triple integrals, we are going to have 3 variables. So it's going to be 3 variables, and I'm going to put x, y, and z right here. We are going to focus on the Cartesian form for this lecture. So triple integral is going to be, well, one more integration, right? It's expected. So one more, 3 of them, and we are going to perform the integration over a function of 3 variables. Same multi-variable function, but this time we have z in there as well. And we are going to perform the integration with respect to some differential value, d of something. What about I save some space right here? Okay. So this triple integral is going to be for x, y, and z. And of course we have 3 integration, 3 times function with x, y, z. Perform the integration with respect to some differential, which we don't know what that is by now at this point. D of something. So let's find out about this d. Okay, now let's take a look at the definition we had for the double integral. We are going to add extra dimension to everything we had before, right? So that it becomes triple integral. So we have done that already with the with the integration sign. We add one more variable. Now we are going to add one more dimension to this dA. It used to be differential area. Now we add one more dimension. It's going to be differential volume. So what is missing here is V. Okay, so we are going to perform the integration with respect to differential volume. And it's going to be over integration domain, and it used to be this R region right here. So this one is supposed to be volume in the space. So you can put V right here, but it's not so popular to use this notation, so we use D instead, just domain. But you need to keep in mind that when you see triple integral like this and you see this D right here, it corresponds to volume in space. And it's 3D. And you can see it right here. Illustration is right here. This D that you see in here, object, is the integration domain for a triple integral. Now let's take a look at this dV right here. Differential volume. Let's take a look at the details of this dV. So once again, we are going to do something similar to what we did before with the double integral. This dV comes from this small step in x direction, something like this. Okay, dx, and small step in y direction, just like before, and we have this rectangle. But now we have a small step in z direction too. So it's going to be this dz, and it becomes a cube like this. So there you go. The volume of this cube is going to be dV. Okay, so you can make a note that dV right here is going to be equal to the volume of this cube. It's either in dx, dy, dz, or you can change the order of the product, equal to dy, dx, dz, and many more. You can make a note right here that all the combinations. And also make a note right here that this is the volume of small piece in the integration domain, D. Similar to what we had with the double integral. So let's take a look here. Small step in x direction, it's going to be this right here. Oh, by the way, this is the whole integration domain D. The blue object, the green object right here. And then we have this small step in x direction. Okay, x direction right here. This is dx. Small step in y direction. This is dy. And small step in z direction, dz. And when you combine all of them, it becomes this cube. Okay, and there you go, you have this dv right here, the volume of this small piece in the integration domain. Okay, now back to the triple integral. It has a physical meaning just like the double integral, so let's take a look here. It's going to correspond to something, and we are going to add one more dimension to the definition that we had earlier with the double integral. So let's take a look here. Here with the double integral we have a volume, right? Something in 3D already. So this time around it has to be something in 4D. Okay, so you can make a note right here. This corresponds to some value in 4D. Of course, this is not easy to visualize. Not easy to visualize. But when it comes to 4D, it's going to involve 4 quantities. So you can make a note that anything that involves 4 quantities in the space involves 4 quantities. We can use this to study the properties of object in the space. Something like this. You can use this to study the mass of a solid with varying density. Mass of object with varying density, and many more applications, but I'm not going to focus on that right now. And we can also do the same thing as what we did up there. We can set this function value to be equal to 1, just like above. This f of x, y, and z can be set to 1, and it's going to be corresponding to something with something similar to this, area of R. But this time around you add one more dimension to everything. It's going to be volume of D. So basically it's going to be the volume of this green object right here if you set the function value to 1. Okay? Now this is just similar to what we had before, but this is going to be 3D. Okay, that is the overview of the double integrals and triple integrals and the comparison between them. So now the most important thing is this dv right here that is going to be a little bit different. So keep in mind that this is something in 3 dimension, and now your integration domain D is also in 3D. Now let's take a look at the formula of this triple integrals in general. So as you expect, it's going to have this triple integral, integration sign 3 times. Okay, and you are going to perform this on a multi-variable function with 3 variables, x, y, and z, and of course you have this dv. So when it comes to this dv, you have all these combination, right? dx, dy, dz, dx, dz, dy, dy, dx, dz. Alright, dy, all 6 of them, dy, dz, and dx, and more. Let me add 2 more. Also we have this dz, dx, dy, and last one, dz, dy, dx. Okay, 6 variation, and you need to pick one. Depending on the situation, sometimes some orders are more suitable to for your problems. So there is no right or wrong here. You need to pick the more suitable one based on the situation that you encounter. Alright, so what about I chose one order right here. I am going to choose a dz, dy, dx. So let me choose this one, dz, dy, dx, last one. And let me put that right here, dz, dz right here, dy, and dx. So this is the general form of the formula of the triple integral. Okay, what about I put the black box? Okay. right now. Everything is gone. Let me erase again. Sorry about that. So we are going to have this box right here and also here. Okay. Now when you see something like this, you are going to perform the integration 3 times, right? So you know right away, integrate. You have to integrate 3 times. And you are going to work from the inside to the outside. You work from the dz first, integrate with respect to z first. Alright, and when you integrate with respect to z, you are going to treat y and x as variable. By the way, this is supposed to be dx. Okay, my bad on that, dx. And then you are going to perform the integration with respect to y later for the second one, and then during this you are going to treat x as a constant, and then you proceed to the last one. Okay, inside to outside, just like we did in double integrals. Okay, now the order is not the problem. The problem is the boundaries. So we need to determine all these question marks right here. The boundaries for z. So let's take a look at the first one. First, integration with respect to z. So z equal to what? Right? Starting point for z variable. Endpoints for the z variable equal to what? Now for y, you need to determine this. Y equal to what? Starting point and ends at what value? Same with x. Last one, x equal to what? Starting point and ends at what value? You need to determine all these unknowns. And you are going to run into 2 scenarios. First scenario is when the boundaries, all these unknowns, are given to you explicitly, directly. Alright, first scenario, all the boundaries given to you explicitly or directly. Okay, in this case, it's going to be more simple. Explicitly. This one is supposed to be simple because you don't need to determine anything. You just need to perform the integration 3 times, working from the inside to the outside. It's supposed to be simple to solve. But the tricky part is going to be the second scenario. This one, when the boundaries are given to you as a shape in the space. Basically, indirectly. Boundaries given to you indirectly as shape in the space. So this is going to be shape, 3D shape, as 3D shape in space. Okay, and this is going to be harder to solve. Okay, and we are going to look into the examples of both scenarios. But first of all, I am going to give you a guideline on the second scenario, which is supposed to be harder to deal with. So let's take a look at that in the next slide. This is going to be going to help you when you encounter the second scenario. So once again, we are going to have this triple integral, something like this. I'm going to use all this space, 3 of them. Okay, and we are going to perform the integration. In this case, I'm going to set the function value to be equal to 1. Alright, and this, with respect to, I'm going to pick one order, which is dz, dy, and dx. Okay, by setting this function value to 1, it means that this is going to correspond to the volume. This is going to be a volume of the integration domain D. So we have this D right here. And right now that we have the order of the integration, like dz, dy, dx, we need to find out about the boundaries of all of them. So here we have to find out about this z, the boundaries for z, starting at this and ends at this. Okay, and same with y, second one, right? Y equal to what? And ends at what value? Same with x. Okay, and last one. So let's find out about all these unknowns. Okay, so by the way, this one right here, we set it to 1 arbitrarily, okay, to make it a volume. Okay, this is function of x, y, and z. So let's find out about this. And I'm going to give you this guideline. And it's going to require 6 steps, right? So here we are going to have 6 steps, guideline, to deal with second scenario. Okay, when boundaries given as object, and we need to determine all these boundaries by ourselves. Okay, so let's start with this object on the right hand side. So let's take a look here. So first of all, in order to find out about all these unknowns, first step is to sketch. You need to do this always. You need to sketch the integration domain in the space. Without a shape, you can't determine anything. First of all, sketch D, because we need to see all the sides of the object. Very important. And we got it right here. So let's assume that we have done with the sketching. So we are going to move to the second step. All right. We need to determine the order of the integration. Order of integration. And as I told you, there is no right or wrong when it comes to dz, dy, dx or other orders. So you have to pick one in the beginning. It's based on your experience. So in this case, we have picked dz, dy, dx just to try it out. So here we have done it. So we have this z first, and then y later, and x for the last integration. So there you go. That is the second step. And we got it right here. You can try something else. It's not wrong. So number 3, next step. You are going to sweep the first variable. Integrate or sweep. Sweep or integrate. Well, I'm going to stick with sweep. First variable. Okay, and the first variable is going to be z right here in this case. But if you pick other orders, you can choose other variables. In this case, it's going to be z. Okay? We are going to sweep this z between 2 surfaces on the integration domain. All right? Between 2 surfaces. Okay, this is the keyword. Keep in mind, this is very important. We are going to sweep between 2 surfaces of D, on D. How is that going to work? So let's take a look here. On the figure on the right hand side. Okay, let me change this. I want to make this a little bit smaller. On D. Okay, so we are going to sweep the first variable, and in this case it's going to be z. So we are going to sweep in this direction, plus z direction, right, to the positive value of z. So we are going to sweep this 2 surfaces. So let's take a look at the first one. So we have this bottom surface of this object. So let's take a look here. This one is the bottom surface of this D. Oh, by the way, we are looking at this integration domain D right here, sort of like a cylinder, but with curvy top and bottom. So this one is the bottom surface. So make a note right here, this is bottom surface. Okay, and we have this top surface right here. Okay. Alright. So we are going to sweep the first variable between 2 surfaces, and it's going to go in this direction, plus z. So it's going to be something like this. From the lower surface to the top surface. lower surface to top surface all the way through. Okay, so there you go. With this illustration, you can see the boundaries for the z variable. This is going to be the lower bound. The bottom surface is going to be the lower bound for the z variable, and the top surface is going to be the upper bound of the z variable. So we are going to use these two surfaces as the boundaries for z. We are going to use them right here. Okay, so let's take a look at the bottom surface, the lower limit of the z variable. Lower limit of z. And as you can see here, this is a surface in the space. So we can express them in terms of a function with two variables. And you can see it right here. f1 of x and y. And we are going to set it to be equal to z. So there you go. We got the first unknown right here to be equal to the bottom surface of this object. And it's going to be equal to z equal to this surface in the space, bottom surface, f1 of x and y. There you go. Now, next one is going to be top surface right here. This top surface is going to be the upper limit of your z variable. As you can see here, z sweep until to this point and it stops. So this, we are going to express this surface as a function in the space. So it's going to be a function with two variables. Z equal to another function, f2 of x and y. Okay, so let me make a note right here. Lower bound for z. This one is the upper bound for z. So there you go. This f2, function of 2, is going to be the upper bound, so we know that upper bound right here has to be changed to z equal to f2 of xy. So let's put that right here. Z equal to f2 xy. Okay. You can call this, well, I don't want to call it upper surface or the lower surface because sometimes the rotation happens and it's not always at the top or the bottom. So I'm just going to leave it as the upper bound right here. So there you go. We got the first two unknowns. Now let's work on the step 4. Step 4 is a little bit strange, but we are going to find the projection. Okay, so next thing, we are supposed to find the projection of this object of D onto the remaining variables, onto remaining variables. And in this case, we have worked with the z, so the remaining variables are going to be x and y. So here is going to be x and y. And this, it means that it's going to be xy plane. We are going to find this projection of this object on xy plane. And xy plane is right here. So xy plane, this. And we are supposed to find the projection. Projection is like shadow. So we are going to find the shadow of this on xy plane. So let's imagine that we have this light source up here, a torch or a lamp, and it shines light, and we get this shadow of this object on xy plane right here. So you are going to get this shadow. Let's assume that this is the shadow of this object on xy plane. So there you go, and we are going to call this shadow projection R. So we are going to call this R. And now next step 5, we are going to sweep the second variable. Sweep second variable. And let's check out which variable are we going to do that on. And it's going to be this dy. Alright, so we know it's going to be y right here. So second variable. And it's going to be between, this time around, it's going to be between two curves. Two curves in R, in the projection. So this time around, it used to be two surfaces, right, that we did before. Now it's going to be between two curves. So let's take a look here. We are going to sweep y variable, and it's going to be in this direction, positive y. All right, we are going to sweep in this way. So it's going to be something like this. Sweeping in y direction on the projection. Okay, I don't like this. Let me change that. It's not parallel to the y-axis, so that's why I need to fix that. Okay, this should be better, right? Something like this. So you are going to sweep it like this. And as you can see here, you sweep between two curves. And this is the first curve. I'm going to call it, in this case, it's going to be the left curve. Sweep to the right curve. Okay, and with a curve like this, you can express it as a function of one variable. The first curve is going to be this, y equal to g1 of x. This corresponds to the left curve. Left curve. Okay, and this one, sweep to y equal to g2x. This is going to be the right curve for this situation. So you can make a note that this one is the right curve. So there you go. G1 of x right here is going to be the lower bound of the y variable. Okay, this one is going to be lower bound for y. And this g2 of x is going to be the upper bound. Upper bound for y. Okay, there you go. So we found the bounds for the y variables, and we are going to use it right here. Let's change this unknown into something that we just found. Okay. All right. Let me fix that. Okay, so lower bound is going to be this g1 of x. Y equal to g1 of x. To the upper bound, which is the g2 of x. Y equal to g2 of x. Okay, now we move to the last step. We are going to sweep the last variable. So, step 6, we are going to sweep last variable, third variable. And as you know, in this case, it's going to be x variable. Okay, and this time it's going to be over the whole range of this x on the projection R. So this one is supposed to be x over whole range on R. So for x, as you can see here, x is going to span from this A right here to B right here. We are talking about the whole range of R. So we are talking about this starting point for x and the end point for x. And as you can see, start at A and ends at B. So this one no longer unknown, and we can put x equal to b. Right, x equal to b. A right here, starting point, and ends at x equal to b. So there you go. So these are the 6 steps that you need to do in order to determine all these boundaries that you need. Keep in mind that the shape can rotate because it depends on the order of this integration. Sometimes it's dx, dy, dz, so you have to do this differently. But in the end, you need to follow this guideline. It's the same thing over and over again. Now that you have seen this guideline, let's apply it to some examples in the next slides. In this example number 1, we are supposed to calculate this triple integral. And as you can see here, it seems like all the information that we need is already given to us. Starting with the order of the integration, we know that we need to perform the integration with respect to z first, x later, and then y for last. What about the boundaries? Boundaries are given to us too. The lower bounds for zxy is already there. Alright, 0, 0, 0. And the upper bounds for all the variables are here. So as you can see, all the information, we have them. So this fits into the first scenario when all the information is ready. So number one, boundaries. First scenario, boundaries are given explicitly. Okay, so we don't need to go look for them. All we need to do is to perform the integration 3 times, working from the inside to the outside. So this is going to be the simpler version of the triple integral problem. So let's start right here on the left hand side. So first of all, let's take a look at this 4y to the power of x squared. This one is the multivariable function f with x, y, and z as the variables. So let's make it clear that this is the function that we are going to work on. X, y, z equal to 4y e to the power of x squared. Even though z is not present in the function, that is okay. Alright, so let's start with the triple integral right here. So we are going to perform the triple integral. Okay, and with this, for this multivariable function 4y e to the power of x squared, with respect to z first, then with respect to x, and last with respect to y. And for the boundaries, start with the z variable. Z starts with 0, ends at z equal to x. Okay, x starts at 0 and ends at x equal to 1. Y starts at 0 and ends at y equal to 1. Okay, so let's work on this one. And we are going to work from the inside to the outside. So the inside one is this integration with respect to z, which we are going to treat x and y as constant during this process. Treat x and y as constant. Okay, so let's work on this one right here. So we are going to integrate this with respect to z, and as you can see here, there is no z in this expression. So this whole term is going to be treated as a constant. So whole term is going to be constant right here. Nothing changes. 4y e to the power of x squared. And then z shows up because we integrate a constant with respect to z. And we are supposed to evaluate this at 2 values of z equal to 0 and z equal to x. And we are supposed to integrate this still twice with respect to x first and then with respect to y. For x, start at 0. I am going to take out these variables from the integration sign to save some space. So this x starts at 0 and ends at 1. Alright, and y starts at 0 and ends at 2. By now you should know that this 1 right here and 0 right here is for x, and 0 right here and 2 right here is for y, based on the order right here. Okay, now this x goes in as z. Okay, so evaluate this. Goes in as z, so I'm going to get this 4yx, okay, e to the power of x squared, minus this 0 goes in as z equal to 0, so the whole term goes to 0. So I have this term right here, and I need to integrate this twice with respect to x first and then with respect to y. At this point, it's a double integral, and we have done a lot of this already, right? X start at 0, ends at 1. Y start at 0 and ends at 2. And we are going to perform the integration from the inside again, this time with respect to x, which means we treat y as constant during this step. Okay, now let's try to integrate this. And as you can see here, we see 2 locations of x, right here, down here, and another one up here. And as you can see, these 2 x's belong to different subfunctions. The first one belongs to polynomial of a power of 1, and this one belongs to exponential, which means that you need to apply some technique or trick in order to solve this. This is not going to be just a simple integration. So some technique that you can use. First one, substitution. Okay, and you can try by parts. Okay, I'm going to start with the easier one always, right? Substitution. Looking at this first one with the order of power of order 1 and this one with the power of order 2, there is a chance that they might cancel, right? So I'm going to try this u equal to this x squared. I'm going to try to get rid of this complex term. So with this, I diff with respect to x, du with respect to x, I get 2x. And with this, I get dx equal to du over 2x. And now I am going to apply this substitution right here into this place. So let's continue over here. Okay, this is going to be equal to, right, let's put everything in. Integration of 0 to 2, same thing. This one's still the same. We haven't done anything yet. So 1, 4, yx. I'm going to put xy right here. Looks better. Now e to the power of x squared. I want x squared to be equal to u, like this. So at this point, this is going to be e to the power of u. Let's use red for that, u. Now dx right here, I am going to use this instead. dx equal to du over 2x. So it's going to be du over 2x. And I still have this dy remaining right here. And as you can see, we can perform some cancellation right here. 2x and this 4x, this becomes 2y e to the power of u. So what do we have right here? Let's clean this up. 0 to 2, same thing. 0 to 1, and we have this 2y e to the power of u. Integrate this with respect to u and then with respect to y. Okay, now we are supposed to integrate this with respect to u. As you can see here, this is exponential of u. It's going to be easy. Nothing changes. So we are going to get this 2y e to the power of u, right? Nothing changes. And we are supposed to evaluate this at two values of x equal to 0 and x equal to 1. We still need to integrate this with respect to y from 0 to 2. And as you can see here, we are supposed to evaluate at x equal to 1, but we still have u right here. So let's put this back. U equal to x squared. So I'm going to put it right here. Repeat right here, 0 to 2. So 2y, we substitute this back. It's going to be e to the power of x squared. Alright, and now we are supposed to evaluate this at x equal to 0 and x equal to 1. Integrate with respect to y. So 1 goes in. Alright, so this is going to be equal to 0 to 2. 1 goes in. What about I put 2y in the front? Okay. Right, 1 goes in. We have this e to the power of 1. That's e. And then 0 goes in. That's e to the power of 0. That's become 1. Okay, minus 1. And we are supposed to integrate this with respect to y. Okay, and this is supposed to be easy because we only have one variable now, just a single integral. So this is going to be equal to 0 to 2, and we have this 2y squared over 2. Oh, this should be gone already. Alright, y squared over 2, and constant still there, e minus 1. And we are supposed to evaluate this at y equal to 0 and y equal to 2. And let's continue over here. Equal to 2 goes in. Oh, by the way, this can cancel. Very nice. So 2 goes in. Right here it becomes 4. Okay, so we have this 4 e minus 1, and then with this 0 goes in, everything goes to 0. So there you go. We have this. Well, I don't need this, right? Let's just put it right here. This equal to 4 e minus 1, and that is the answer for this example number 1. Okay, let's move to example number 2 in the next slide. Here we need to find the volume of a tetrahedron. which is basically a 3D object made of 4 triangles, and we know all the vertices right here, 4 of them. First one at the origin and 3 more. And we are supposed to use the triple integral to find the volume here. So to use the triple integral to find the volume, we need to set the function value f of x, y, and z to be equal to 1. And we are going to rely on this formula right here. Volume of integration domain D equal to the triple integral of the function value, which is equal to 1 in this case, because we want the volume to be the result of this integration. And we perform the integration with respect to the differential volume, dV, okay, over the integration domain D. As you can see here in this formula, we don't have any information about the boundaries, which means that this is the second scenario when the boundaries are given to us indirectly. So, second scenario, boundaries of the integration of each variables given to us indirectly as shape in the space, as 3D object. Okay, so in order to use this formula, we are going to rely on the guideline that I gave to you earlier, which has 6 steps. So we are going to start on that right here. So we are going to use the guideline over here. So let's write down right here, guideline. So let's start with the first one. The first one is to sketch the integration domain D in the space. Let me fix this. Okay. So first of all, we need to sketch integration domain D in the space, and let's assume that we did that and it shows up right here. So here, let's take a look at the tetrahedron. So the first vertex is right here at the origin. So let's take a look right here. First vertex. Next one is 1, 1, 0 right here. Next one is 0, 1, 0, which is right here. Last one, 0, 1, 1 right here. And when you connect all of them, you are going to get this shape in the space. Okay? Along the edges. Okay, give me some time to work on this. So there you go, that is tetrahedron. And as you can see, it's made of 4 triangles. Alright, so we have sketched the integration domain in the space. And next thing that we are going to do is to determine the order of the integration. Order of integration. Since we don't know anything much about this shape, we are going to try something. So you can pick one right here for this dV. So what about I pick this order? So this comes in random. So I'm going to try to use this dz, dy, and dx. Okay. So I try this. There is no right or wrong order here. I just pick one. So in this case, I'm going to pick this order, z, and then y, and then x. You can pick something else. Right, number 3. We are going to sweep the first variable now. Sweep first variable, and that's going to be z. Okay? So let's write down right here. Sweep z between 2 surfaces, and it's going to be between f. Let me fix that. Between 2 surfaces, f1 of xy. Okay, and f2 of xy. So we need to find these 2 in the graph. And that's why we need to sketch this object. f1 of xy and f2 of xy. So we are going to sweep z, right? So it's going to be sweeping in this direction, positive z. In this direction, positive z. Okay, so we are going to sweep in this inside this object, and it's going to go like this. Okay, going in positive z direction. Okay, from lower surface to the upper surface, something like this, all the way through, right here. And as you can see here, with this kind of sweeping, we are going to what about I change, well, that's okay. Let's use red for that, the sweeping pattern. So we are going to try to find this first surface right here, f1 of xy, which is the start of the sweeping pattern. And it's going to be this right here at the base. Okay, starting of the z variable. And as you can see here, it's on the xy plane. And if you want to find the expression for this, it's quite easy. It's going to be z equal to 0. And we are going to set this to be equal to function of 1 xy. What about I write it down here? This one right here is going to be z equal to 0. Okay, and equal to, and we set this to be equal to the function f1 of xy. So there you go, we found one. Okay, so let's write down right here. What about I change this a little bit so that I can put everything on this guideline. So first of all, f1 xy is going to be equal to 0. So there you go, that is the first surface. So this between two surfaces. Okay, we found the first one. Now let's take a look at the top surface, and it's going to be this surface right here. The ending of the sweeping pattern is going to be this plane. Okay? It looks a little bit messy, but I think you can see the shape that is going on. Starting from the base right here. Oh, I'm sorry. Base down here and ends at the top right here. Okay, so we are supposed to find the expression for this blue plane, and it's already given to us, luckily, which is right here. Y equal to x plus z. This is the equation for this plane, and we can move things around so that z equal to y minus x, and we set this to be equal to the second function, second surface, f2 of x and y. So there you go, we have found f2 of xy. Well, the thing is, what if this is not given to us? What if this is unknown? Is it possible to use the information we got from the problem to find this equation? So let's try to, let's take a look here. So instead of having this equation, we are going to find this ourselves. So we are going to do that by using two vectors. So first of all, let's put this f2 xy right here, and we found it to be equal to y minus x. But let's assume that we don't have the equation right here. What are we going to do? So first of all, we can create this vector from origin to this. Okay, let's use black for this vector. Okay, and we are going to call this vector u. So this one is going to be vector u, and since we know the coordinate right here, we know that the vector u is going to have this form 1 1 0, right? And we use this vector right here from this vertex origin to this 0 1 1, and we are going to call this vector v, and this vector v is going to be equal to this component form of 0 1 1. Well, because we know the coordinate right here, 0 1 1, is going to be the same thing here. So with these two vectors, we can perform the cross product, and in the end, it's going to create this vector right here. Okay, so let's assume that we have this vector as the cross product of these two, and we are going to call this n, vector n. It's going to be orthogonal to this vector v and orthogonal to this vector u, to both of them. And we are going to use this vector n to find the equation for the plane. So let's try to do that. So vector n right here, this is special, is going to be equal to the product of u and v, and it's going to be equal to this I, j, and k. So vector u is 1 1 0, and vector v is 0 1 1, and this is going to be equal to, so down here we get I and plus k, and minus, going up we have this j. Alright, so it's going to be equal to I minus j plus k for this vector n. And we are going to use the coefficient in front of each component here, 1, minus 1, and 1, to create this equation for the plane. So it's going to be first 1 of x minus, right? Second one is minus 1 of y plus, last one is coefficient is 1 of z, equal to some constant which we don't know. Since this is 1, I am going to erase them. X minus y plus z equal to c. At this point, I am going to put one point into this equation, any point on the plane, and I'm going to use this easiest one, 0, 0, 0. I put this one 0 in, 0 in, 0 in, and then I get this c to be equal to 0, right? Okay. I solved the equation, I got c to be equal to 0. So in the end, we have this x minus y, x minus y plus z equal to 0. Or you can express this as y equal to x plus z. Y equal to x plus z. Which is going to be the same as this that we just erased. Okay, so if you don't have that given to you, that's fine. You can find that yourself. So that is 3. Now let's move to next step, which is the finding the projection. Projection onto the remaining variables. Okay, so we have done the z variable. The remaining variable is y and x. So we are going to find the projection on xy plane. Okay, on xy plane, remaining variable, and it's going to be in this x and y plane right here. To find the projection, you need to find the shadow of this object on xy plane. So let's assume that we have a light source up here. Okay, let's assume it's right here, and you try to find the shadow of this onto xy plane, onto the ground, and it's going to show up as this triangle. This is the shadow, the projection of this object on xy plane. So there you go. Projection, and we are going to call this projection R. Okay? We call this R. Alright, now next step. We are going to sweep the second variable. Sweep second variable, that's going to be y. Okay, that's y between two curves. Alright, this time it's two curves on R. Two surfaces on D right here. Okay, so we are supposed to find two curves here. First one is g1 of x, the remaining variable, equal to what? And second one is g2 of x equal to what? Okay, so let's find that. So first of all, let's take a look at this shadow projection right here. Okay, and we are supposed to sweep the second variable, which is y, and we are going to sweep in this direction, positive y, right? Sweeping in this pattern, in this direction, is going to create this pattern, right? On the projection. What about I use green? Maybe it's easier to see. So we are going to sweep this in this direction, and it's going to create this sweeping pattern. Okay? From left to right, left to right. There you go. So with this sweeping pattern, you can see two curves between them. First one is right here on the left hand side. This is going to be g1 of x, right? Starting of the sweeping of y variable. This one is going to be g1 of x. And the endpoint for the sweeping pattern right here on R is going to be on this curve or this line. Okay? So this blue one is going to be g2 of x. Okay, so let's start with g1 of x. We are supposed to find the expression for this line in the space. So as you can see here, we have x-axis right here and y-axis right here. We know right away this line is x equal to y, which means that this g1x is going to be equal to x as a function of x, right? And we need to make use of this. So there you go. We have this g1x equal to x. Okay, equal to x right here. What about g2 of x? Let's take a look here. g2 of x is y value, right? So y value is constant along this line and it's equal to 1. So there you go. With this y equal to 1, that is this line. Oh, by the way, this is supposed to be y equal to 1. So we can set this g2 of x to be equal to 1 because y is constant along this line equal to 1 and right here. So we found g1x and g2x. And the last step, 6, sweep last variable, x over the whole range. So let's take a look at this sweeping pattern here. So we are going to sweep in this direction, positive x. And as you can see here, over the whole range of this projection, x start at this point at the origin and ends at right here at 1. So we know right away that a is going to be equal to 0. A equal to 0 and b equal to 1. From this we get that starting point for x is going to be a equal to 0 and then b equal to 1. So there you go. We have found all the boundaries for z, y, and x. Z is right here between two surfaces, and y is right here between two lines, two curves, and x is right here, just two scalar, right, two values. Okay, now we are going to make use of these informations and let's solve the triple integral. So we are going to use all the boundaries here. So let's start with the triple integral. Okay, up here, and we are going to perform the integration with function equal to 1. And as you know, we have determined the order of the integration to be dz first, dy next, and then dx for the last. And we found the so let me put this z equal to this one z between us. We sweep the z variable between two surfaces. Z start at the lower bound, which is f1 of xy. Upper bound is f2 of xy, and y has the lower bound of g1 of x, upper bound of g2 of x. Okay, and for x start at a and ends at b. Okay, and we are going to put everything in. So first of all, let me put all the information back here. f1 of xy is equal to the lower surface. It's going to be equal to 0. f2 of xy is going to be equal to y minus x. Okay, and g1 of x is going to be equal to x. And g2 of x is going to be equal to 1. A equal to 0 and b equal to 1. So everything is ready. So let's work right here. Now let's put everything in. Triple integral of 1 dz, dx, dy, and then dx. First start with the f1, and it's going to be right here. So I'm going to put everything in. 0 to y minus x. For y, from x to 1. And for x, it's going to be from 0 to 1. Okay, let's start doing the integration here. We are going to start from the inside. Integrate this with respect to z. We treat y and x and y as constant. Okay, so integrate 1 with respect to z. This one is easy. So we are going to get just z right here, and we evaluate this at two values of z. Z equal to 0 and z equal to y minus x. And we still need to integrate this twice with respect to y and x. x1, same, 0, 1, still the same. Now, this values goes in as z right here. So this is going to be equal to y minus x, and then this one goes in 0, so nothing happens. So I can keep this y minus x, and I need to integrate this. dy dx, y from x to 1, and x from 0 to 1. So I need to integrate this. This is double integral. Integrate this with respect to y. So here, you can make a box right here. Okay, what about I erase this? Okay, and 1 right here. So this one we are going to treat x as constant. Okay, let's integrate this with respect to y. I'm going to get this y squared over 2, right? And then I integrate minus x. I'm going to get minus xy, because x is a constant to y. So there you go, and I need to, once again, evaluate this at two values of y. Y equal to x and y equal to 1. Okay. Alright, then I need to integrate this one more time from 0 to 1 with respect to x. Okay, so first values goes in, 1 goes in, I get this 1 over 2. So this equal to 1 over 2 right here. And then 1 goes in right here, I get minus x. 1 over 2 minus x, that is the first term, minus the second term. This one goes in as y, right here and right here. So I am going to get this x squared over 2 minus x squared. Alright, and I'm supposed to integrate this with respect to x, starting from 0 and ends at 1. So let's combine all these terms. I'm going to get 1 over 2, alright, minus x, and then minus plus x squared over 2. Okay, cancel these terms. And after that, you can perform the integration with respect to x. Integrate this with respect to x. 0 to 1, and this dx right here. Okay, so this should be easy. Integrate this with respect to x. We get this x over 2 minus x squared over 2, and minus plus x cubed over 6. Okay, and we evaluate this at two values of x, and x equal to 0, x equal to 1 right here. And 1 goes in, alright, everywhere. And we are going to get this 1 over 2 minus 1 over 2 plus 1 over 6 minus second term, 0 goes in, of course it goes to 0. Same thing here, same thing here. So we have this 0. So in the end, we have this equal to 1 over 6 because these two cancel each other. So there you go. We have this 1 over 6 as the volume of this tetrahedron. Since this is volume, the unit is going to be unit cube, cubic unit. Okay, so that is the answer for this example number 2, and we can move to example number 3 in the next slide. And it turns out that example number, okay, let me take a look here. We are still on example number 2, I'm sorry. But here we are going to try something different. Okay, before that we tried on this problem, we used this integration order. Previously, we try this order, z, what about I put this, dz, dy, dx. And I told you that there is no right or wrong in terms of the order of the integration. You can try something else. So here we are going to try something else. So we are going to try maybe dy, dz, dx this time. And let's see what's going to happen when it comes to using the guideline. Okay, so we are going to do this instead, dy, dz, and dx, different order. Okay, this is supposed to be we tried. We did that. Okay, and now we try something different. So we are going to perform the integration with respect to y first, and then z, and then last with x. So we are going to apply the guideline without having to write down everything. So I'm going to start with the sketching, and the sketch is already here. Same object, same tetrahedron. Now the order of the integration is already here. So we determine it's going to be y, z, and x. Now we are going to sweep the first variable, y, between two surfaces. Okay, this is going to be different than what we had before. So let's start with that. Sweep the first variable. So you can make a note right here. Since this is important, I'm going to put it right here. Sweep y between two surfaces. Okay, so this is supposed to be surfaces. So let's take a look how it's going to be different this time. Since we are going to sweep y first, we are going to sweep in this direction, positive y. And let's take a look at this object right here. We are going to sweep throughout the object using this sweeping pattern. From left to right, over the whole range, the whole object. Okay, something like this. So we are supposed to find the left surface and the right surface. And as you can see here, the left surface is going to be this one. The left surface, the starting point of the sweeping pattern, is going to be on this plane. Okay, starting from this plane, and we sweep in y direction, and we end at this plane right here. Okay, all right, give me some time to work on this. So there you go. Okay, so we are sweeping between from the green plane to the blue plane. So that's how it looks when we sweep the y variable between two surfaces. And this green right here is going to be, so let's assign this to be f1 of x and z this time. Okay, and we also need this f2 of x and z. f1 of x and z is going to be this plane, green one, and of course it's going to be equal to this y value, right? So it's going to be equal to x plus z. So we can use this right away. Equal to x plus z. So this one is f1 of x and y. Okay, we need more space right here. It's too cramped. So this is going to be f1 of x and y equal to that, the equation for the plane, and that is x plus z. Now, the right surface is going to be this one. Okay, let me highlight this a little bit better for both of them. Okay, this one is the right plane. Okay, so this one is going to be y value, and as you can see here, this one has a constant value of y equal to 1. Okay, so this f2 of xy is going to be equal to a constant value of y, which is equal to 1. So there you go. You found the boundaries for y. One is right here, left surface, and this one right here is the right surface. Okay, you can make a note right here, left surface, and next one is the right surface. Okay, now next thing we are going to do is to find the projection of this object onto the remaining variables. The remaining variables are going to be z and x. So we are going to find the shadow on xz plane. For right here, projection on xz plane, and it's right here, z right here and x right here. So in order to find the projection, we are going to put a light source up here. So with this light source, you are going to create this shadow of this object, and it looks something like this on xz plane. It's going to be this shadow with the shape of a triangle. Alright, so let's highlight this. This shadow shows up once you put a light over this object. So there you go. This is the projection, and we are going to call this R. Okay, so next thing we are supposed to do is to sweep the second variable, and that is going to be z. Sweep z between two surfaces. Oh, I'm sorry, two curves. Between two curves, and we are supposed to find these two curves. And these two curves are going to be g1 of x, okay, equal to something, and g2 of x equal to something, and we are supposed to find that. So first of all, let's take a look at the sweeping of z variable. It's going to sweep in this direction, positive z. So we are going to get this sweeping pattern on this projection R, going up in positive z direction. So with this sweeping pattern, we are going to see the two curves between the arrows. So we are going to get this right here for the lower line. Okay, and for the upper curve or line, it's going to be this one. So the end point of the sweeping, the end line is going to be this one. So we are going to use this green line as the lower bound for the z variable. And as you can see here, this line has a constant value of z equal to 0 here. So this one is easy. 0 right here is going to be g1 of x, the starting of the sweeping pattern for z variable. So this one, let's set it to be equal to 0. Now we are going to sweep and ends at this line, right here at this boundary. And we are going to use the equation for this line to represent g2 of x. And we have the equation for this line right here, x plus z equal to 1. And we can express this in terms of z equal to 1 minus x. And we can set this to be equal to g2 of x, right, in terms of x variable. So this is going to be 1 minus x. And last one, 6, is going to be for x variable, the range for x. And as you can see here, the range of x starts at 0 and ends at 1 again. So sweep x. Okay, so this is sweeping x variable, and we have this a equal to 0 again and b equal to 1. So there you go, we got all the information that we need. So let's construct the triple integral. Since I have limited space, I'm going to squeeze things into this one slide. So it's going to be this. V, again, is going to be equal to triple integral, okay, of this same function, 1, because we want to find the volume. And we try this order, dz, dy, dz, dx. And we found all the information. First, the surfaces in terms of y variable. So we sweep from f1, which is x plus z, to f2, which is 1. For z variable, it's going to be between this g1x and g2x. Oh, by the way, for y variable, we use this f1 and f2 right here. And that's why we have this x plus z and 1 right here. Now for z, 0 to 1 minus x. So we have this 0 to 1 minus x. Now for x, from 0 to 1. So let's put 0 to 1 right here. Now let's work on this integration. So this is going to be equal to we integrate this with respect to y. Of course, we are going to get just y out of that. And we need to evaluate this at two value of y, x plus z as the starting point and ends at 1. Okay, and two more. Integration 0 to 1 minus x, and x from 0 to 1. dz, dx. And now this one goes in as y. This one goes in here, and we get this 1 right here as the first term. And then the second term, y equal to x plus z, goes in right here, and we get the second term equal to minus second term x plus z. And I'm going to combine all these terms right here to be just 1 minus x minus z. So let me erase this. Just 1 minus x minus z. Alright, and we are supposed to integrate this twice with respect to z and x again. Same terms, 0 to 1 minus x, and for x starting at 0 and ends at 1. Okay, so we are going to integrate this with respect to z. This is double integral. So we are going to treat x as a constant right now. So this is going to be equal to, first term, integrate 1 with respect to z. We are going to get z out of that. Integrate minus x with respect to z. Of course, this is constant to z. We are going to get minus x z. Integrate minus z. We are going to get this minus z squared over 2. And we evaluate this at two values of z. Z equal to 0. And this one, z equal to 1 minus x. And we still need to integrate this with respect to x, starting from 0 to 1. Now this z equal to 1 minus x goes in here, right here, and right here. Many terms here. So we are going to get something like this for the first term. So let me fix this. Something like this. Okay. Equal to, first term goes in, we have this 1 minus x for this first term. This one. Now second term, this one right here, it's going to be minus x, 1 minus x. Now last term, minus z squared over 2, it's going to be 1 minus x squared over 2. And we need to integrate this. Oh, by the way, this is not the end. We still need the second value, right? Right here, z equal to 0 goes in here as z, goes in here as z, and same here. As you can see, it's going to go to 0. So we have this minus 0, which we don't need that. So let's erase that. Okay, so we still need to integrate this with respect to x as the last variable from 0 to 1. Now we have all these terms. Let's combine them. So I'm going to work right here. So here, 1, we have this 1 minus x minus 2x. Combine them, and we have this minus x times x, so it's going to be plus x squared right here. Now last term, it's going to be 1 minus 2x plus x squared over 2. Okay, still messy, so let's work on this. So this is going to be equal to, so constant 1 and minus 1 over 2 right here, it's going to be just 1 over 2. Now minus 2x right here, we have minus 2x, and we have this minus x, right? With the minus sign at the front, it's going to be plus x. So here I have this minus x. Okay, and last term, plus x squared minus x squared over 2. So this one is plus x squared over 2. Alright, this looks better. So let's continue the calculation right here. Okay, the space is tight. So this is going to be equal to integration of this term that we just found, 1 over 2 minus x plus x squared over 2, and we integrate with respect to x, starting at 0 and ends at 1. So this is going to be equal to x over 2, alright, minus x squared over 2, plus x cubed over 6. Evaluate this at two values of x, 0 and 1. And we have this 1 goes in, here, here, here. And we have this 1 minus 1 over 2 and plus, oh, sorry, this 1 over 2. plus 1 over 6, and 0 goes in. And as you can see here, everything goes to 0, minus 0. So this cancel, 1 over 2 minus 1 over 2, and in the end we have this equal to 1 over 6, and since this is the volume of the tetrahedron, once again the unit of this is going to be cubic unit, unit cube. It's the same as the previous example that we did with the different order of the integration. Previously we tried this dz, dy, dx, and we got this 1 over 6 cubic unit. Here we try different order, dy, dz, dx, and we still got the same number. So as I told you, there is no right or wrong when it comes to the order of the integration. If you don't know which one to go for, just pick one and work on it.